So this is EE 619, lecture 22. So we saw that a latch can be implemented in the simplest term using a mux. So let's say I implemented a latch in this configuration. So what latch is this? Is this a positive latch or a negative latch? So this is a negative latch. Now we also saw that the same implementation can be thought of as an inverter driving a bistable element. So you can have an inverter with a switch here, followed by two inverters connected back to back, but again through a switch. Now, to get the same implementation as shown earlier, what should I connect here? Should it be clock or clock bar? So we want a negative latch, right? When clock is 0, the data should come to Q. So this has to be clock bar. And this is then clock. Because when clock is 1, we want this feedback path to be on. Okay. So now can you quickly implement a positively edge triggered flop? Again, what is the clock polarity connected here? So this is clock bar. This one has to be clock. This one is clock. And you have clock bar. Right? And we were trying to look at what is the setup time, the clock to Q delay, and the hold time for this flop design. Right? And we were going to look at it in terms of the delays of the individual components, such as the inverters and the transmission gates. Now, before I get into the calculation, we are making some assumptions in doing this analysis. So can you comment on the assumptions we are making? So we are making assumptions related to the clock waveform. We are going to assume that we have ideal clock waveforms. So there most likely won't be a recording for this. The recording is done through cloud. So with multiple disruptions, the recording would have been broken. So which means you have to pay a lot of attention to the class. It might not be very clean. it's going on. So we'll see. Okay. Notes are. Okay. So the first assumption we are making is that we are dealing with ideal clock waveforms. That means the rise time and fall time of the clock is 0. We have instantaneous waveforms like this. Right? The second assumption we are making is that the clock skew is 0. So this means that there is no delay between the clock and the clock bar signals. Okay. So typically you will either generate your clock bar from clock using an inverter, or it's possible that both the clock and clock bar signals are generated somewhere globally, and then it is getting routed to your design, in which case it's not necessary that both of them have the edges at the same time, right? But for now, we are going to deal with the assumption that clock skew is 0. So if you have a clock signal like this, so if this is your clock signal, your clock bar signal is going to match the edges exactly with it. Okay. So these are the two assumptions that we are working with. So now I had asked you to figure out what is it that we require to ensure that the data is reaching the queue correctly when this data is changing sometime before the clock. Because that is the condition that will now help us to identify how to define the setup time for this flock. So any suggestions? So I can remind you what all answers I got last time. Some of you said that it should reach this node. Others were very confident that it should reach QM. Some of you said that it should reach here, etc. So what is that defining criteria that we should use to define the setup time? Let me nudge you to the answer a little bit. So all of us agree that the setup time constraint has to come from the first latch, the master latch, right? So let us look at only the conditions affecting the master latch. So I'm going to consider, let's call this node here as N1. This is N2. Sorry, this we will call as N2. And this is some X. I'm going to consider all the capacitance associated with N2 as some C2. And all capacitance associated with this node as some Cx. Okay. Now, let us consider the scenario where you have a rising edge in clock, right? And let's say the data is also rising very close to the clock edge. Okay, so the data has been 0 for a long time before that, and the data remains 1 for a long time after the clock edge. Now, under these conditions, please sketch out the waveforms at N1, so this node, X, and N2. So you can assume that the D has changed just before the clock edge. So what happens to N1? N1 will have a falling edge, right? What happens to X? So the value of X is going to follow N1 as long as the clock is 0. So it will start to fall down, right? And N2, so N2 will follow X after 2 inverter delay. So it has not yet seen the effect. So it will hold the previous value, which is 1. Right? It has not seen the effect yet. Now that the switch is closed, what happens to X? Charge sharing with? With what? I mean, so CX and C2 will charge share, right? And it will charge share that goes as the input to the I2. And then you have the positive feedback kicking in. And because the value of X has just started to decrease, right? Once you charge share, it will slightly go up again. And then the positive feedback will kick into place and it will eventually come to VDD. Do you see what has happened? And also you can potentially have a dip provided, yeah, you can have it. Depends on how much before it has. So it's possible that you will have some dip lengths. So now if your D was changing slightly before this, let's say somewhere like this, the dip in X would have been larger. The dip in N2 also would have been larger. And at some point, because of this charge sharing, it's entirely possible that the voltage at this node goes into the midpoint voltage. And if it becomes a midpoint voltage, your bistable element will now enter into metastability. And once it enters to metastability, whether it comes out as 0 or 1 depends on the noise, right? And how long it takes to come out of that metastability also depends on the type of noise present in the system, which is something we really want to avoid. Are you following? So what this boils down to is to ensure that the data is correctly sampled by the first latch, we have to set up the data such that when the feedback kicks in, there is no confusion, right? There is no race condition happening between these two nodes when the feedback kicks in. That is, we want to avoid this sort of charge sharing, or in other words, both CX and C2 should have the same potential. Okay. So now can you tell me what should be the delay TSU? So how far before this clock edge should my data be set up? Such that the data that we want to be sampled reaches this node. So what is TSU? Can you tell me in terms of I1, TG1, etc., delay of these blocks? So it should be DI1 plus delay of the transmission gate. Yeah, it is in the path, right? So delay of I2 plus delay of I3. Is this okay? So that is what we discussed. If it reaches till I2, and if C2 is not charged to the required value, when the feedback kicks in, you have a problem. But if it has reached C2, then you are guaranteed that you will not have a problem. In the other case also, it's possible that you can get the correct value at the output, but it is risky. It can easily enter into metastability. The data is coming just before the clock edge. By the time the data has crossed the first inverter, would the... So I understand your question. This is, I just wanted to show you how the CX and C2 being different can cause a problem. So this you can, so if I say that it is happening before the data has reached here, then there is no question about being able to sample it, right? It doesn't even reach this node. So whatever is the previous value will come out. But the The deciding criteria for us is that Cx and C2 should be at the same value. Otherwise, you can have charge sharing and possibility of entering into metastatic. So now, if this is clear, can you comment on the clock to Q delay for this flop? After the rising edge of the clock, assume that the data has been set up before the setup time, right? It has been set up nicely. You have a rising edge in the clock. How long does it take for that data to come to the queue? So I4, TG3, and I5. Is the question clear to everyone? So this is your clock edge, right? Let's assume that your data is changing well before the rising edge of the clock. Now you know that corresponding to this rising edge, you will have a transition in Q. So this rising edge in the clock is going to cause a transition in the Q. And this delay from clock to Q is what we call as TCQ. Right? So the question is, after the rising edge of the clock, how long do you think it will take for us to see the data at Q? So one answer I have got is I4 plus TG3 plus I5. Any other answers? Plus I6. So why I6? For it to hold, is it? Okay. So after the clock has risen, after you have a rising edge in the clock, after it has risen, what state is the second latch in? So tell me whether L1 and L2 are opaque or transparent. L1 is? L2 is transparent. So is that a concern now? Did you follow?
Yeah.
Okay. So it's clear that I6 is not a concern, right? Because this switch is anyways off, the feedback path is not going to affect us. So it is I4 plus TG3 plus I5. Right? Now, what if I tell you that I can just deal with TG3 and I5? I4 also need not be accounted. Does that make sense? I3 and? Correct. So we said that the data has been set up much earlier, right? Before the setup time. Now this guarantees that the data has already reached here, which means there's a very high chance that the data has already reached here. Right. So now when you have a rising edge in clock, you only need to account for the delay from this node to the output. It depends. So in saying dTG3 plus dI5, we are assuming that the dI5 has the capacitance taken into account in its delay. So we can write our TCQ as D of TG3 plus dI5. Is this clear? Now, I want you to think about what would be the hold for this circuit, the hold time for this circuit. Why 0? No, it's okay. So after the edge, okay. Okay. So should it be 0 or should it be a negative value? It should be negative of the first inverter, right? It can be actually negative of the first inverter and the first switch. Okay, is that clear? So again, let me remind you about the hold time. So this is your clock edge. Let's say your data was low earlier, and then you had a rising edge after the clock edge. Now, ideally, you want your Q to remain as 0. You don't want this edge to be sampled. Okay. So now the question is, how close can I bring this D to the clock and still have 0 come at the output? Okay. So the first answer I got was it can easily come till this point. It can easily come till the rising edge of the clock. Why? Because once you have the rising edge in the clock, this transmission gate switches off. Therefore, it doesn't corrupt the feedback circuit. Is that clear? So now the question is, can I pull this data to this side of the clock and still have 0 sampled? Right? That is possible if you ensure that the change in data doesn't reach this point. So you could have your data change before the rising edge in the clock. As long as this new data doesn't propagate to this node, your feedback circuit is going to hold the previous value once clock goes to 1. Is that clear? So for this particular circuit, now your T hold will be equal to negative of the first inverter plus the first transmission gate. Why do you say it is risky? Including TG1 is slightly on the edge. So now it depends on how you are modeling it. If you assume that if the switch closes, I mean, if it is off. Yeah, so all of these are for hand calculations. If you are characterizing a flop, there are other methods that you follow in simulations to do it. Now, this sort of hand calculation is useful when you want a quick estimate, right? Or when you want to compare multiple architectures. So that is when this method is useful. But for reporting the setup and hold time and clock to queue delays, there are other simulation methods, which also we will cover. Okay, so now what should we do? We started off calculating all of this based on 2 assumptions. Now let us tackle these assumptions one by one, right? So let us bring clock skew into the picture. So now we are going to assume that we generate our clock bar from clock using an inverter. So if this is my clock signal, my clock bar ideally should have been like this. Right? But now it is going to get shifted with some delay. So we will assume the same positive edge triggered flop for our calculations. In which case, can you tell me the state of L1 and L2 in all of these scenarios? Right? So let us start with something that is known. So when clock is 1 and clock bar is 0, during this phase, what is the state of L1? What is the state of L2? So L1 is opaque and L2 is transparent. So the same thing comes here. And here you have the opposite. You have L1 as transparent and L2 as opaque. What do you think happens during this overlap? So in this particular overlap, you have both clock and clock bar as 1. So what should we call it? Both are opaque, but what should we call this overlap as? 1-1 overlap. So this is called as 1-1 overlap. So now during 1-1 overlap, what is opaque and what is transparent? Both are opaque. Why do you say that? During this, yeah. Okay, let me quickly sketch out the flow. Okay. So when clock is 1 and clock bar is 1, you mentioned that they are opaque. Why? L2 should be transparent when clock is 1 and clock bar is 1. Is that the... So now let me ask you, how are we implementing the switch? If you are implementing it as a transmission gate, and if both are 1, what happens to it? Yeah. So now if both of them are 1 of the transistors, then every transmission gate is going to be on, right? Similarly, if both of them are 0, again, 1 of the transistors, then every transmission gate is going to be on. So now during the overlaps, what comment can you say? Everything is on, right? So you can have a direct path from D to Q. So now this is what we called as a 1-1 overlap. This is what we call as a 0-0 overlap, right? We have to, 0-0 overlap also, everything is on. You directly have a path from data to Q. And this is a problem, right? So now we have to analyze for both 0-0 overlap and 1-1 overlap and make sure that our flop still behaves like a flop. It doesn't turn into a different logical element. Okay, so we'll start with the 0-0 overlap. We have assumed a positive edge triggered flop, which means our sampling edge is the rising edge in the clock, right? So now this 0-0 overlap is associated with the non-sampling edge. So let me draw the same figure on the board so that we can make use of both the schemes. This is a 1-1 overlap. And this is the 0-0 overlap. Now, in this period, L1 is, what is L1 here? Okay, it's transparent here. L1 is opaque, L2 is transparent. And here we have L1 as transparent and L2 as opaque. So now to analyze the 0-0 overlap, we will take a state of the output before, during, and after the overlap period. As long as things don't go after the overlap period, so before and after the overlap period, we should be good to go, right? So we are analyzing the 0-0 overlap. And this is the non-sampling edge. So before the overlap, L1 is opaque, right? What this means is, even if my D changes here, it doesn't affect any of the nodes after this. So change in D doesn't affect Q, doesn't affect QM or Q. right? Now, during the overlap, we have a possibility for having a change in D race all through to Q. It can shoot through and reach Q. Is this okay or is this undesirable? Why is this undesirable? It's a wrong sampling edge, right? If it's a positively edge triggered flop, you shouldn't see any transitions in the queue during the falling edge, right? So this is a non-sampling edge. So this is clearly something that we do not want to see at all, right? Now what happens after the overlap? L1 becomes transparent, but more importantly, L2 is becoming opaque, right? So if you don't want to see a change in Q during a non-sampling edge, what is the constraint that we have to make sure? D should be held constant. But this is a non-sampling edge. How do we even tell the consumer or a customer that don't have any transition in D, right? Is it something better? Any other constraint that you can play around? So after the overlap, L2 is opaque, right? So we don't have to worry about L2, the output Q changing, if we ensure that the QM has not changed, right? So what comment can you make about the duration of this 0-0 overlap such that I don't have a problem? It should be smaller than. So let's say this is T00 overlap. Should be smaller than what inverter delay? So this was TG1. Okay, so before the overlap, the data could have come till here. Now, during the overlap, the data shouldn't shoot through and reach till QM. Is that clear? Sorry? It might cross I2. Is that the constraint?
What's your answer? Delay of TG1 and delay of I2.
No, I have not given you an answer. I'm asking.
I'm saying till only TG1.
Till TG1. Why not till, let's say, QM?
Because when the down clock will be on, right?
So for now, let's just assume that the feedback strength is smaller than the direct path strength. Okay. Second latch is opaque. What is the problem? It reaches till QM. No, that is fine. So what is the point where it can reach and still not cause a problem at the output? Second latch is opaque, meaning which switch is off now? This one, right? TG3. So the changed input shouldn't cross TG3. Right? During the overlap. So the overlap period has to be smaller than delay of TG1 plus delay of I2 plus delay of I4 plus delay of TG3. Delay of I1 because before the overlap, the data could have reached here. Right? So you look at it in terms of the switches available. Is this clear? So if you don't ensure this condition, then it is possible that during the non-overlapping, during the non-sampling edge, you can see a transition at the output, which means you are not selling a D flip-flop anymore. It is something else. Right? So now this is a functional issue. You have some variables to play around. During the simulation, you will be able to find out what is the 0-0 overlap that you are seeing in terms of the clocks reaching the flop. Then you can play around the delay of these transmission gates as well as delay of I2 and I4 to make sure that this constraint is met. Is this clear? Any questions on this? Okay. So now can you follow the same approach and analyze for 1-1 overlap? So 1-1 overlap is the sampling edge. You have to look at what happens before the overlap, during the overlap, and after the overlap. Right? So before the overlap, what is the status of L1 and L2? So L1 is transparent, L2 is opaque, right? And again, because this is a sampling edge, we have assumed that the data is stable before TSU. Which means even though L1 is transparent, it is okay for us because the stable data is what is coming through. Okay. Now, during the overlap, of course, you have this direct path from D to Q. And after the overlap, L1 has become opaque and L2 has become transparent, right? So now what is the criteria that we need to meet in terms of how much 1-1 overlap we can handle? So let's say now during the overlap, data changes, right? So during the overlap, if data changes, what should we ensure? It doesn't cross. Is it enough if it doesn't cross TG3? Because after the overlap, L2 is transparent. It should not reach QM, right? So which means it shouldn't even affect the inverter before that. Do you see? Because after the overlap, L2 is transparent. This whole path is on. So it shouldn't even reach this node. Therefore, the maximum T11 overlap possible is D of I1 plus D of TG1. Is this clear? And this is, as you can see, is slightly more difficult to meet. Earlier, you had more delays which you could play around with. This is even smaller than that, right? But here is the fact that this is a sampling edge comes to our help, right? This is a sampling edge. We can put constraints on setup and hold. So if we tell the customer that they shouldn't change the data during the overlap, then we don't have to. So we find out what this 1-1 overlap is. Then we tell the customer this is the hold time for us. So now it's up to the customer to make sure that the data is stable for this for a set time duration and during this overlap for a hold time. So we basically ensure that the whole time for the flop now is greater than T11 overlap. Is this clear? So earlier we saw that the same flop had a negative hold time, but when you have a 1-1 overlap where the rising edge is your sampling edge and the clock bar is a delayed version of clock, we can have a positive value for the hold time. At least the same magnitude, it can be slightly higher. Is this clear? Okay, good. So we will have a surprise quiz in the class based on whatever has been taught today. I'll give you 10 minutes to revise. So can you close the last door? Lock it from inside. Based on whatever was yeah. I'll give you time to think. Don't worry.